Did you know that there's an energy source more predictable than the sun and more consistent than the wind, one that follows a rhythm older than human civilization itself? I'm talking about the ocean's tides. While solar power depends on daylight and wind power on weather patterns, the rise and fall of the tides is as reliable as clockwork. But how do we turn the steady push and pull of the ocean into electricity? And if it's so promising, why aren't we hearing about it every day? In this video, we'll dive into the mechanics behind tidal power plants, explore their remarkable potential, examine the challenges preventing them from going mainstream, and discuss the latest innovations and research that could finally bring tidal energy into the limelight. First, let's set the stage. What exactly are tides? They're the regular rise and fall of sea levels caused primarily by the moon's gravitational pull, and to a lesser extent the sun's combined with the Earth's rotation. Most coastlines experience 2 high tides and 2 low tides every day. This cycle is not only ancient, it's also remarkably predictable. Scientists can forecast tidal patterns decades into the future with great accuracy. While solar and wind energy fluctuate, tidal patterns are essentially built in. Imagine a renewable energy source where you know, to the hour, how much power you'll get next week, next year, or even in the next decade. So how do we convert these rhythmic movements into electricity? Let's start with tidal barrages and lagoons. Picture a dam-like structure built across a bay or estuary. During high tide, water flows into a basin. As the tide recedes, the stored water is released back into the sea through turbines generating electricity. The same can happen in reverse, harnessing both incoming and outgoing tides. A classic example is the Lorance tidal power station in France. Operational since 1966, it has a capacity of around 240 megawatts and generates approximately 500 gigawatt-hours of electricity per year, enough to power tens of thousands of homes. It was a groundbreaking project at the time and still stands as a testament to the viability of tidal energy over the long term. Another large-scale example is the Sihwa Lake Tidal Power Station in South Korea, with a capacity of 254 MW, currently one of the largest tidal installations in the world. These projects prove that tidal range technology can deliver steady, reliable power on a significant scale. Another approach is through tidal stream turbines, which harness the kinetic energy of fast-flowing underwater currents, similar to wind turbines but submerged. These turbines don't require massive dams. Instead, they sit on or near the seabed in areas where tidal currents are strongest, often between islands or in narrow straits. The Maygen project in Scotland is a notable example. Once fully realized, it aims to reach nearly 400 MW miles of capacity. Already it has begun feeding power into the UK grid. Maygen's tidal stream turbines operate under the waves out of sight, capturing energy as water rushes past twice a day. The key advantage here is a potentially lower environmental impact and greater site flexibility compared to big dams or lagoons. What makes tidal energy so intriguing? 1. Predictability. Tidal energy's biggest selling point is reliability. Grid operators value knowing exactly when and how much power will be produced. This predictability can reduce the need for costly energy storage or backup plants that kick in when the sun isn't shining or the wind isn't blowing. 2. Low carbon footprint. Once installed, tidal plants have minimal direct CO2 emissions. Over their operational lifetime, often several decades, they provide a stable source of clean electricity, reducing reliance on fossil fuels. 3. Longevity and durability. Structures like the Lorance station have run for over half a century. Tidal devices properly maintained can keep generating power for decades, spreading out capital costs and ensuring long-term energy security. 4. High energy density. Water is about 800 times denser than air. This means even moderate tidal currents can generate more energy in a smaller area compared to wind. In some prime locations, a few turbines can produce a surprisingly large amount of electricity relative to their footprint. Globally, the theoretical potential of tidal power is estimated to be in the hundreds of gigawatts. If even a fraction of that potential is harnessed, tidal energy could become a key part of the world's renewable energy mix. But if tidal is so promising, why isn't it everywhere? The short answer is cost. Right now, tidal energy is generally more expensive than solar or wind. Early-stage estimates put tidal's levelized cost of energy, LCOE, anywhere between 15 and 30 cents per kilowatt-hour. Meanwhile, solar in prime locations has dropped to around 3 cents to 5 cents per kilowatt hour in recent years. Wind, both onshore and offshore, has also become substantially cheaper. This cost gap is one of the main hurdles. Tidal projects often involve challenging marine construction and building foundations that can withstand powerful currents, corrosion, and storms. The industry needs to refine turbine designs, improve materials, and scale up production to achieve economies of scale. As more projects get built and lessons are learned, costs could decline, just as they did with solar and wind. Some experts suggest that with enough R&D, tidal power could become cost competitive within the next 10 to 20 years. Maintenance is also tricky. Sending divers or specialized equipment to repair submerged turbines in strong currents is complex and expensive. Changing water flow patterns can affect local ecosystems. For instance, tidal barrages might alter fish migration routes or sediment transport, impacting fisheries and coastal habitats. While tidal stream turbines are thought to be less intrusive, research is ongoing. Environmental assessments and long-term monitoring are crucial to minimize harm. Tidal power is site-specific. You need regions with strong tidal ranges or fast-flowing currents. The Bay of Fundy in Canada, parts of the UK and France, and certain straits in Southeast Asia are excellent candidates. But not every coastline is suitable, limiting widespread deployment. Solar and wind have enjoyed decades of subsidies, R&D, and massive scale-up, driving their costs down. Tidal, still in its relative infancy, must compete with these well-established and increasingly affordable technologies. So where is tidal energy headed? Countries like the UK, Canada, South Korea, and even China are investing in research and demonstration projects. Governments and private investors are increasingly interested. In the UK, the government has provided contracts for difference for tidal projects, signaling policy support. The European Commission's strategic plans for marine energy include tidal, and organizations like IRENA, International Renewable Energy Agency, monitor developments and provide guidance on scaling these technologies globally. Engineers and researchers are exploring lighter turbine materials, advanced coatings to reduce corrosion, and floating platforms that allow easier installation and maintenance. Modular designs could enable mass production, driving down costs. Some R&D efforts focus on integrating tidal energy with battery storage or pairing it with other renewables to create a more balanced and reliable grid. As the world grapples with climate change and looks for stable, carbon-free electricity, tidal energy's predictability becomes increasingly valuable. Today, solar and wind dominate the renewables landscape due to cost advantages, but their intermittent nature still poses challenges for grid stability. Tidal energy, with its guaranteed daily cycles, could serve as a stabilizing force, an anchor that smooths out the variability of other renewables. Imagine coastal communities that rely on a combination of solar, wind, and tidal. When the sun sets and the wind calms, the tide might be reaching its peak flow, ensuring a steady stream of power. In regions like the Bay of Fundy, known for some of the strongest tides in the world, tapping just a portion of that kinetic energy could supply a significant share of local demand. Tidal power plants are not theoretical. They've been producing electricity for decades at places like Lawrence, yet they've remained overshadowed by the meteoric rise of cheaper solar and wind technologies. But as the global community pushes for deeper cuts in emissions and more reliable renewable grids, the ocean's tides stand ready, predictable, unrelenting, and clean. In the coming years, we may look back at these early projects and realize that what once seemed niche has become an essential piece of the puzzle. With the right investment, research, and scaling, tidal energy could transform from an underdog to a key player in our sustainable energy future. If you found this video informative, hit the like button, consider subscribing, and let me know in the comments, do you think tidal energy will make waves in the global energy mix?